So good morning. So we finally arrived to the last day of this celebration of IMPA's 70th anniversary. And I feel humbled and honored to introduce Vinicius Ramos. Vinicius did his master's in UFRJ back in 2007. And then he went to Berkeley, University of California at Berkeley, to do his PhD, and he finished it in 2013. Then he passed a period of 2 years in the Université de Nantes for a postdoc, as a postdoc. And in 2015, he became our colleague here at the IMPA, first as a postdoc, and 2 years later as member of our faculty. Vinicius has, soon after he started IMPA, he was awarded this prestigious grant from Serra-Pideira. He's a specialist in symplectic geometry, and will talk about the matter conjecture, billiards, and symplectic inequalities. Please, Vinicius.
Thank you, Jorge. Yeah, first of all, I want to say that I'm very humbled to be here, to be invited to speak at this conference. Among so many amazing mathematicians, I feel quite humbled to be here, and also honored to be working at IMPA, which is an amazing institution in this wonderful country that we live in. So yeah, when I came back to Rio in 2015, I was very excited to be here, and I just couldn't wait. I mean, I think many of us who have spent time abroad know what it's like to have the eagerness to come back to this country with its amazing things and its problems. So I am very happy to be here and to tell you a little bit about the story of things that I think about. So in this talk, I'm going to try to explain many different things and how they intersect. So first of all, if I write too small, please let me know. I'm very happy to give a Blackboard talk again. So I quickly decided not to do slides. But if I start to write small, please let me know. Okay, so I'm going to start with an old conjecture from convex geometry. So suppose I take a convex and compact set in Rn. And suppose that it's centrally symmetric. So that means just that minus k equals k. One thing that you probably know, or you might know about, is that given a set like this, you can consider its polar body. So that's just a set of points in Rn whose inner product with everything in k is less than or equal to 1. So for all y in k. So this is equivalent to basically considering a norm in Rn whose unit ball is given by k. So you can always do that. And then this would be the ball in the dual norm, the unit ball in the dual norm. Okay. And one thing that you can notice is that given a invertible linear transformation, when you multiply your set by, when you multiply k by this matrix, the polar of that gets changed in a simple way by minus the transpose, the inverse of the transpose. Which means, you can think about the easiest thing. Like if you take your set, you contract it, then the polar is going to get expanded. So when you pair them up, k and its dual, you see that there's something that's preserved. And sort of one of the easiest things to see that it's preserved is the volume. So the volume of k times the volume is the product of the volumes. The product of the volumes is preserved under multiplication, under this transformation of GLN. So now you can call this number something. So I'm going to call this m of k. And you can ask about how big can this be and how small can this be. I mean, clearly, it's not very hard to make it very small or very big. because if you try to scale, the other one scales against you, and then that doesn't work. So you have to really change the shape of k to make this invariant bigger or smaller. And it's not very hard to see, and in fact, you can prove that if the rounder you make k, like if you start, for example, with balls in the LP norm, it's not very hard to see that for LP, basically the largest this number is for p equals 2, so the round ball. And then the worst this number, and then the smallest this number can be is when you do p equals 1 or p equals infinity. So you kind of get a sense that the rounder your convex set, the larger this number is, and the kind of less round and pointier your convex set, the smaller this number is. So based on that, you can ask, so question, so what's the min and what's the max in this class of convex set? So the question is that really that this number is always bounded by this invariant of the round ball, so Bn, and it doesn't matter what the radius is, and it's bounded below by, say, the cube. Okay, so that's a question in print. So that was a question that maybe, I don't know, if Mahler was the first person to ask, or if it was asked before him. But anyway, we can actually prove this inequality relatively simply. It's not extremely easy, but so this is what was known a long time ago. So in Blaschke, in 1923, he proved the upper bound for n equals 2 and 3. And then Santalo generalized his method a little bit in 1949 and proved the upper bound for n greater than or equal to 4. And the process is using some kind of symmetrization procedure. It's similar to the proof of the isobarometric inequality. So you take something that's not symmetric and you kind of do it slice by slice and you make it more symmetric. And then eventually you converge to like an ellipsoid or directly to a ball. But if you get an ellipsoid, that's good enough because it's the same as the ball. So basically, not only can you prove this, but you can also prove the equality is only obtained for ellipsoids. Yeah?
So Vinicius, what is the polar of the square?
What?
What is the polar of a square?
Of a square?
Yeah.
It's a rotated square in dimension 2. So in higher dimensions, the cube is the unit ball in the L infinity norm, and the polar is the unit ball in the L1 norm. So for the polar of a cube is a cross polytope, an octahedron, a regular octahedron. Okay. So anyway, so there is this upper bound is not too hard, and then Mahler proved so that for n equals 2. A relatively direct proof that the lower bound holds for n equals 2. And that equality holds only for parallelograms. Parallelograms. So squares and linear transformations times squares. Because the dual of a square is a square that's just rotated 45 degrees. Okay, so, and it's actually not a very long paper and not extremely hard. I mean, Mahler was an amazing mathematician that did work in many different fields. Oh, and I forgot to say this was in 1939. And then he asked, what about in higher dimensions? What about the lower bound in higher dimensions? And I can spell out what this number is so you see. So the question was, or the conjecture, so this is Mahler in the same paper, 1939. He asked, if you have K, a convex set with those conditions, so compact, convex, and centrally symmetric, is it true that the volume of K times the volume of its polar is bigger than or equal to that number for the unit disk, which you can compute? It's just 4 to the n over n factorial. for n greater than or equal to 3. And the progress in this conjecture is kind of interesting. So people have been able to show that this number is bounded below. So I don't want to give the whole story because I'm going to talk about symplectic geometry. But I just want to say that Kuperberg proved that this is true for, instead of 4, he got a pi. So this was, I think, in the 2000s. So it is true, Kuperberg, that this holds with a pi to the n over n factorial.
More than one Kuperberg.
Yeah, so it's the sun.
Great
So,
son, Greg.
oh, great sun, okay.
No. His name is the guy who proved that. It's Greg Kuperberg.
Greg, yeah.
That gave us.
Yeah.
His mother.
Yeah, Greg, yeah, so he's the son and there's a mother. Oh. Yeah, and I think that he definitely has papers with his mother, right? There's Kuperberg, yeah. So anyway, he proved this with a pi. So of course, and then of course, there are no sharp, examples of equality because it's not believed it's true. But anyway, and then there are many other things, but basically, this conjecture, the only real progress in this conjecture in its full for the conjecture with the 4 was only made in 2020. So this is by Irie, Shibata. I think it was 2017 that the paper was on the archive, and it was published in 2020, which is that the conjecture holds for n equals 3. And it's like a 60-page paper with a lot of very insightful, calculation stuff. But there's not like there's not a lot of theory that's used here. I mean, it's relatively elementary. I mean, if you can call it methods. So from convex geometry. Okay, and then that's the state of art of this conjecture. So why am I telling about this? I want to motivate some other things in symplectic geometry involving billiards and other systolic inequalities. And you'll see that, I guess it's the strategy math. If you can't solve a problem, you come up with a harder problem. And then you just change the angle, and maybe you can solve it. Or maybe not, and then you just keep making it harder. Anyway, so what you can see is that, we're taking this conjecture, we're taking the product of 2 volumes. So you could consider the product of the 2 sets and look at its volume. So if you look at k times k dual, the first thing you observe is that it's contained in R2n. And if you see even dimensions, you either think complex or you think symplectic, which apparently is the Greek word for complex. So you think symplectic. So what is symplectic? So if you have your R2n, I mean you can talk about the history of Hamilton, but I will skip Hamilton for now. Because I usually talk about him. And instead, I'll just jump directly to the symplectic form. So we have this 2 form, which is the sum of dxi dyi. And that's a 2 form on R2n. And symplectic geometers are usually interested in the structure of R2n. So the questions are, sort of what's the structure of R2n with this symplectic form? And then questions such as, what are symplectic invariants? So what are invariants of this structure? So what are transformations, embeddings, or whatever that preserves this guy? And this is related, this has its roots in Hamiltonian dynamics. Okay, so one of these invariants is called capacity. So I'm going to just jump directly to what symplectic capacities are. And I'm going to restrict everything to R2n. I don't need to talk about more general manifolds today. So if you take a subset of R2n, a symplectic capacity is something that will assign to a subset a number that could be 0, and it could also be infinite. But usually it's finite. I mean, if it's compact closure of an open set, a non-empty open set, it'll be a finite number. But in some cases, it can be infinity. And it has 2 basic properties. One is that it scales. When you put an r in front, it will scale quadratically. So this is for every dimension. So that means that it's a two-dimensional invariant, even though your space is higher dimensional. And then if you have an embedding of one set into another that preserves the symplectic form, I'm going to write like this. It's not a very standard notation, but for the stock, I'm going to put the omega 0 saying, having a smooth embedding from x1 to x2 that preserves the symplectic form, meaning that the pullback of omega 0 is omega 0. Then I have an inequality. So this capacity of the first one is less than or equal to the capacity of the second one. So it obstructs symplectic embeddings. OK. Up to here, you could just consider the zero function. And then usually we require some non-triviality, but I'll say that in a little bit. So we usually require some non-triviality to make it interesting. Triviality. OK, so let me give you the first example, which is kind of the base case. Oh, I got small. Yeah, sorry. I'll write 3 again there with an actual condition. So the first example, and maybe even, well, I don't know if it's the main example, but it's the first example is what's called the Grum of Width. So the Grum of Width is the following thing. You consider the supremum. You look at a two-n-dimensional ball that embeds into your space X, and you look at pi r squared of that radius. So given if there is an embedding of a ball into your domain, you look at what's the largest pi r squared such that this ball embeds. OK? Oh, and I should say one thing, which is that when I talk about a symplectic embedding, I'm always assuming the dimension is the same. So it's a codimension 0 embedding. And I know a lot of people study submanifolds here. So I'm not looking at high codimensional submanifolds. So this is all same dimension. OK. So I'm assuming X is set in R2n. OK. So one thing that it's easy to check that this Grum of width of a ball is just pi r squared. That's kind of completely obvious, almost completely obvious, because if you have a symplectic embedding, then you have a volume-preserving embedding. So the volume of this is less than or equal to the volume of that. So if it's a ball, it has to be this. But the thing that's really non-trivial, it's a theorem of Gromov, is that this capacity, or this width, when you consider the cylinder, so a 2-ball times R2n minus 2, that this is also pi r squared. This is called Gromov's non-squeezing theorem. So this is called the non-squeezing theorem. And this is not exactly the formulation that he had in his paper, but it's equivalent to prove this. OK? So this is kind of interesting, because I'm taking a set that's very non-compact, in a way, and still this capacity is a finite number. It's equal to the ball. So the ball is right here. And even though I made the set much, much, much bigger, I still have the same capacity, the same Grum of width. OK, so this motivates kind of the quest for looking for other capacities. And this is something that has been done. It was very intense in the late 80s. And then it took a break. And then it picked up again in the 2000s. So now I can actually say what the non-triviality condition that I would require of a symplectic capacity in general, which is that I would require C to, first of all, be positive for a ball, and to be finite for a cylinder. Okay, so this is not the volume. It's like a completely different. It should be a completely different invariant in spirit. And it's not even like a power of the volume, as a power of the volume would satisfy 1 and 2. Like if you take the volume to the 1 over n or something. But that certainly violates this condition. OK. And also, inspired by Gromov's non-squeezing theorem and stuff, you can ask kind of a slightly stronger condition than 3, which is what we usually call normalization. So a normalization that is often required is that the capacity of the ball and the capacity of the cylinder this guy, are both equal. And then we can just set it to be equal to pi r squared. Why not? The area of the disk. OK, so it's this equality. I mean, we always have an inequality here. And we're assuming the weaker assumption that this is positive and this is not infinite. But the stronger assumption, which is normalization, is that they're equal. And you can notice, if you maybe are bored with what I'm saying, you can, maybe it's not so hard, but you can also check that the existence of a normalized symplectic capacity is equivalent to Grumov's non-squeezing theorem. So just constructing this is just as hard as doing that. OK, so now I want to also, again, if you're bored, you can check this observation, which is that if you look at the Grum of Width of any compact set, there's an interesting inequality. So the Grum of Width to the n over n factorial is less than or equal to the volume of x. And this is basically just a computation of the volume of the ball. So because the Grum of Width is given by embeddings of balls, and then you look at the volume of the ball, you have an inequality of the volume of this. The volume of this has to be less than or equal to the volume of that. And then the volume of the ball in 2n, in dimension 2n, is just pi r squared to the n over n factorial. OK, so I told you how to do it. OK, so we have this observation. And so based on this observation, Viterbo made the following conjecture. And looking at many examples. So maybe I'm skipping some of the motivation. But Viterbo conjectured the following thing. And this was in the early 90s, I think. So this was, I don't remember the year exactly, but I'll say early 1990s. He conjectured that for any normalized symplectic capacity, C, and then for a compact and convex set, we have a similar inequality. So C of x to the n over n factorial is less than or equal to the volume of x. So it's actually not so hard to look at non-convex sets and to violate this inequality. But he conjectured this for convex sets. And this is a long-standing open conjecture. So this is still an open conjecture in general. And I should say, I don't want to write this down at this moment, but I should say that you can do something that's similar to the Grum of Width, but with a cylinder. And that's kind of on the other side. So if you look at the cylindrical capacity, which is sort of the smallest cylinder into which you can embed your manifold, that's also symplectic capacity, and it's also normalized. And it's not so hard to see from the normalization condition that any normalized symplectic capacity is in between the Grum of Width, so that's the smallest symplectic capacity, and the cylindrical capacity, so that's the largest symplectic capacity. So if you could show that the smallest one and the largest one are equal, then that means all of them are equal, and then by this observation, then this conjecture holds. But I mean, we only have hope to prove that for convex sets, because for non-convex sets, there are counterexamples. OK, any questions about this? OK, so the next thing I should say is give you an example, or tell you about other symplectic capacities that are not these kind of more trivially constructed from embeddings. So I won't quite give you a full definition, but I will say that so there exists. I'm going to say this theorem is by Ekelund, Hofer, and Hofer-Zender. And this was at the turn of the decade from like late 80s and early 90s. So this is like 88, 89, and this is like 91, 92. So I'm going to say 88 to 92, something like that. They proved the following thing. There exists a normalized capacity that is easy, or Well, let me tell you what it is. Such that for convex sets, for a convex set, x, C of x is the smallest, so the infimum, it's actually, yeah, let me say it. The infimum of the action of a closed characteristic on the boundary. And maybe some of you are like, what are you talking about? So I'm going to define it. But maybe some of you know what I mean by this. So now I step a little bit into the realm of dynamics, which is not my area, but we have to step into dynamics, and I'll tell you what this means. So if you don't know what this means. So no. I'm just asking, I'm saying that if it's convex, then you can compute it like this. And to be completely proper, I should say that it's convex and it has a smooth boundary. So convex, compact with smooth boundary. Okay, so let me tell you quickly what this means. So if you take a set in Rn, a domain, say, that has smooth boundary, then you can look at your symplectic form restricted to the boundary of x, and this actually will have a kernel, and this will have a one-dimensional kernel. So it has a one-dimensional kernel because the symplectic form is non-degenerate, but then you take a hyper surface, then it has to have a kernel, and then this generates a one-dimensional foliation, or if you want, you can choose a vector field. Another approach to this is if through Hamiltonian dynamics, you can see the boundary of x as the level hypersurface of a Hamiltonian, of a function, of a smooth function. So we can always do that for a hypersurface. You can choose a function whose preimage of a regular value is exactly that thing. And then you can look at the Hamiltonian vector field, which is just the symplectic gradient. So another approach is you can look at a function, a smooth function, such that the preimage of 0 is the boundary of x. And then you can look at the Hamiltonian vector field, which is the unique vector field such that omega 0 of xh dot is dh. So this goes back to the 19th century in Hamiltonian dynamics. So given a function, instead of looking at the gradient, so when you have a metric, a Riemannian metric, you look at the gradient. When you have a symplectic form, then you can look at the Hamiltonian vector field. Okay. Or you can just look at this. And then you can look for closed orbits of this vector field or closed leaves of this foliation. And it's not obvious that they exist. But you can prove they exist using kind of basic convex geometry with some functional analysis. You can prove they exist. And then if they exist, you can look at their lengths. So, how do you measure the length? We don't really use a Riemannian metric here, so it's not the Riemannian length, but it's the symplectic action, which basically means, so if gamma is a closed characteristic, then you can say that its action is, you can integrate a primitive of omega, of the symplectic form on lambda. So this is a primitive. So d lambda 0 is omega 0. Or alternatively, you can just integrate your symplectic form over some disk that bounds gamma. That's the same thing by Stokes' theorem. Okay, so then you can take the infimum of that, which will be realized, so it'll be a minimum. Okay, so for example, if you take your cylinder and you make it compact, so you kind of cap it up, then it's not too hard to see that you have a closed characteristic right here, and its action is the area of this disk, pi r squared. Okay? And the same thing for the ball. If I take the ball, I can take all, there are many closed characteristics on the ball. Pretty much every point is on a closed characteristic. And then the area is going to be pi r squared 2. So this is kind of, if you believe in that there is a C that will be a capacity, what I'm showing with this picture is that it's normalized. Okay, so this is an example of another normalized capacity. I didn't tell you how to define it in general for other sets. That's a bit hard. But I think it's already for convex sets, I told you how to define it. And I guess the exercise show that this will extend to a capacity. Okay, so now you could, of course, conjecture something a little weaker, which is that just this capacity, the Eklund-Hoford-Zender capacity, satisfies this inequality. So that's a weaker assumption, so a weaker conjecture. So I'm going to call that the weak Viterbo conjecture. So that just says that if X is a convex, oh, and I can call this guy the minimum action of X. So I can just say that if X is convex and compact, then the minimum action to the n over n factorial is less than or equal to the volume of X. So that's, and this is a systolic inequality. So as you see, if you're looking for smallest things in some class, that's what's called systolic inequality. And it has to do with hearts. And you can ask Lucas to relate this to the systoles and what's the other one? Diastole. Distal, yeah. Okay, so yeah. So what I want to tell you now, I still haven't talked about my work, but I think hopefully it'll get there. I want to tell you how this is related to the Mahler conjecture that I started with. So now I want to tell you about a beautiful theorem theorem of Artstein, Avedon, Karasev, and Ostrover of 2014, that weak Viterbo implies Mahler. So if you followed my story, it's probably not too hard to imagine what X I'm going to pick. So if I want to prove the Mahler conjecture, so let me tell you about the proof. Because in this proof, I use one of the ideas that is kind of at the core of my research in the last few years. So the proof is, consider if you have K a convex, centrally symmetric, compact set, then you consider the X, which is K times its polar. And the question is, can you compute the Eklund-Hoford-Zender capacity, so the minimum action of K times K dual? And what they proved is that this guy is always equal to 4. No matter what K is, you always have that this minimum action is equal to 4. And now, if you take this 4 and you plug it in here, and you know the volume of the product is the product of the volumes, Fubini theorem, then you get the Mahler conjecture. So this implies the Mahler conjecture. And actually, let me take the time to make a comment about this, which is the fact that I'm not saying anything about the equality case. So I mentioned that the equality case in the Mahler conjecture holds, it should hold for a cube, but in fact we can come up with a very big family of subsets that attain the minimum, that are not just cubes. I mean, of course, if you can take a cube and its dual. So the dual of the cube is the cross polytope in higher dimension, so it's the unit ball in the L1 norm, so that will be a minimizer. But we can actually kind of mix it. You can take lower dimensional cubes, take their duals, and take products. So if you start to do that, that will still be a minimizer of the Viterbo conjecture. And those are called the Hanner polytopes. And for the Viterbo conjecture, on the other hand, the conjecture is that this is only maximized for a ball. And we can't do the symmetrization procedure that Mahler did here. It doesn't really work symplectically. So it's kind of interesting because the maximizer here corresponds to the minimizer in the Mahler conjecture. So this is kind of a subtlety, but basically, and actually now I can talk about one of my theorems, which is that if you take the cube, so this is a theorem that I proved with Daniele Seppe from UFI in 2017, I think it was published in 2017, is that if you take the cube times the product of the cube, times the dual of the cube, that this is symplectomorphic, so it's symplectically equivalent to a ball. So to B2n with the appropriate radius. Okay, so if you put, you're basically asking yourself, well, what is going on? This thing is a minimizer of the Mahler conjecture, but then you put on your symplectic glasses, and you're like, oh no, it's a ball. It holds. And actually, Terry Tao wrote about the Mahler conjecture in his blog, a very cited blog post of Terry Tao, and he said he thinks that part of the reason that the Mahler conjecture is so hard to prove is that there isn't a unique minimizer. So there's a unique maximizer. If you do the symmetrization, you kind of converge to a ball. But the minimizer is not unique. So you have all these Hunter polytopes. So it's kind of hard to find a procedure that converges, an optimization procedure that converges to something. But kind of my answer to it is like you forgot to put your symplectic glasses on. Because up to a symplectomorphism, the products that you're looking at should all be balls. So, I mean, it's also part of the conjecture of Viterbo is that the equality case is only for a ball, and that's not proven. But there is no counterexample. So I think it's widely believed that the maximizers are balls. Yeah, so there was a question up there? Well, you can take it 2 factors in dimension 3, but no. So n can be 3, yeah, but 2n cannot be 3. Yes, that's right. Oh yeah, I forgot to say that. Part of the theorem that I said from 2020 is they also proved that the minimizer in the case n equals 3 are only the parallelopipeds and their duals, because the dual of a parallelepiped is not a parallelepiped. It's a cross polytope. It's an octahedron. Yeah. Okay. All right. So now I actually want to give you an idea of this inequality, because you see that this is kind of the key point. So how do you prove this? And to show this, I have to explain how the Hamiltonian dynamics here works. So suppose I have 2 sets, K and L, in Rn, and I will look at their product. So K times L in R2n, and I want to compute the minimum action here. So just to clarify, this is what we call Lagrangian product, because so basically the x variables are in K and the y variables are in L. Okay? And this is particularly important to say if n equals 2, because then there are 2 ways of taking a product. But in higher dimensions, it's not so, it's not, you wouldn't think of something else. But for n equals 2, in 4 dimensions, there's definitely a symplectic product, and then there's a Lagrangian product. And I want to emphasize this is the Lagrangian product. So anyway, where the symplectic form is the summation of dxi, dyi. Okay. So now what I want to do is I want to compute the minimum action. I want to look at this guy. So I need to look at the characteristic foliation on the product. And here I'm going to cheat a little bit, because I told you take a smooth boundary, and then you look at the characteristic foliation, and then of course when you take the product, the boundary is not smooth. But let's ignore that. And I'm going to also to begin with, I'm going to assume that they are both disks. So suppose that K equals L equals a disk. So to make it a little bit simpler. So I want to look at the boundary of D2 times D2. So that, I'm going to draw a picture in one dimension less. So the boundary has two parts. So this and this. And the boundary here, I can write it as the boundary of the disk times the disk, union with the disk times the boundary of the disk. And now, and then there is the union. There's an intersection, which is a solid torus. No, sorry, there are two solid tori, and then there is a torus where they intersect, which in this picture is represented by these 4 points. But anyway, so you should see it as like there are these these two compact three manifolds that intersect on a torus, and that's a corner of your manifold. Okay, so how do you compute the characteristic flow? The easiest way to do it is looking at a Hamiltonian vector field. So you look at a function that whose level set is this boundary. So for example, you take the max of the norm of x, norm of y. And again, I said you take a smooth Hamiltonian. This is not smooth, but we ignore that. And we look at the Hamiltonian vector field. Let me put a square here, and then the Hamiltonian vector field, how do you get that? Well, you can take the gradient, and you can multiply by I. So, and this function is like either this one or this one. So it's not so hard to see if you do a little calculation that the Hamiltonian vector field here is going to be basically either the sum of xi ddyi or yi ddxi. And then you put a minus sign on one of them. There is an orientation thing here. I'm going to do this. So this one is on D2, no, on the boundary of D2 times D2. And this one is on D2 times the boundary of D2. Okay. And then, this is the function was not smooth. So this vector field is not continuous. But the flow, you can actually define a continuous flow. Okay, so let's actually draw the flow, because this is probably the nicest thing I'm going to say. So I'm going to draw, we have to draw flow in a three manifold. That's a little hard to draw, but I'm going to do a schematic picture. So schematic picture is like this. I'll draw two disks, and then on the boundary of this, I'm either in anywhere here and just on the boundary of this, or I'm anywhere here and just on the boundary of this. Okay, so let's start by saying that I am somewhere here. So I am on the boundary of this disk, and I am anywhere in the interior of the second disk. And what do I have to do? I have to follow this vector field, which is telling me you have to move y in the direction of x. So here's my x, and I have to move y in this direction until I hit the boundary. So when I hit the boundary, it's like I'm going through this corner. So I go through the corner. I'm not going to tell you what happens at the corner. There's a discontinuity, but then I, boom, get into the other solid torus, and then I have to follow the other vector field. So now I have to follow the vector field that says, go in the direction of minus y, move the x in the direction of minus y. So then I do this until I hit the boundary again. And then I do this. Then I go back to the original solid torus, and then I have to look at this direction here. And then I move this guy in this direction. And so on and so forth. But it's not hard to see that this angle here, the angle of this angle here, is equal to this angle. And this angle here is equal to this angle. Okay, so this is pretty simple to notice. And then because this guy here is a disk, then these two angles are the same. Which means that what I'm seeing on this disk is a billiard trajectory. And actually, if you continue going on the other one, you also see a billiard trajectory. So you have two billiard trajectories that are kind of coupled in some way. So that's how you get billiards. So basically, the characteristic flow on this bidisk is basically two coupled billiard trajectories on disks. So the characteristic characteristic flow is in a bijection with coupled billiards. And in fact, it's not hard to see that you only need one of them. The other one is kind of implicit, is determined by the other one. And then what I want to tell you is that this idea, you can actually do it for any k and l that are reasonable enough. So say convex. I think even star-shaped, you can do something similar. So if k and l are not disks, then what changes in this picture? So what changes is now, instead of the Hamiltonian vector field, is not going to be given by this because you don't have norm of x and norm of y, and instead you would have sort of the norm k of x and the norm L of y. So sorry, the max of these two. Where k and L are the norms that define, so say you have centrally symmetric sets. So you have a norm that defines the convex set. And then when you look at the Hamiltonian vector field, instead of just having x, you're going to have the normal to k. So this guy would be substituted with the normal vector field, with the ith component of the normal vector field at x, and this one would be the normal vector field to y. Okay, so you have, instead of looking at the position, you just look at the normal. But anyway, you will have a similar flow here, but it's going to be a funny billiard. It's not going to be real billiards on anything. It's going to be what are called Minkowski billiards. So it's like billiards in one set with the reflection law determined by the geometry of the other set. And in fact, if one of them is a disk, then the other one could be another set, like any kind of random convex set. And then the geometry of the bouncing here is going to be round billiards. So it's going to be the regular billiards. So this is kind of, if you do D2 times some K, then the dynamics here is going to be regular billiard dynamics on K. And then on D2, you have some funny dynamics. But the philosophy that I told you about is that actually you can ignore one of them. So to understand the symplectic geometry of this guy, you really only have to understand regular billiards in K. OK, so, and then to finish their proof, now you can just look at basically a convex set, centrally symmetric, times its dual, and show that there is always a billiard trajectory that bounces twice like this. And then because the length is determined by the other norm, the dual to the other norm, you can basically always show that this guy always has length or action 4, no matter what the convex set is. So this is that proof and of how weak Viterbo implies Mahler. So are there any questions about this? I want to make one more comment about the billiard thing, which is that one thing that you can prove directly from symplectic capacities in this interpretation of billiards is that, which is a non-trivial fact about billiards, is what's called the monotonicity. So if you have a billiard table, a convex billiard table, that's contained in another convex billiard table, then the smallest billiard of the smaller table has length smaller than or equal to the smallest billiard of the larger table, no matter what the shapes are. And that is a fact you can prove just using billiards, but it's not so easy. And it's a direct consequence of symplectic capacities, of the monotonicity of capacities. OK, so what I want to finish with is telling you some results about balls. So basically one line of my research is looking at these Lagrangian products and seeing what the theory of billiards can tell us about the symplectic geometry. So I already mentioned that I was able to prove that the product of the cube and its dual is symplectomorphic to a ball. And in fact, what we can prove, and this is more recent, with Ostrover, myself, and Daniele Seppe from UFI, is that you can actually get some other products that don't have to do with the Mahler conjecture, but you can look at a simplex and take the product with a polytope, an n-dimensional polytope. So this is del n, and take the product with a polytope, and this is still a 2 n-dimensional ball. So the case n equals 2, which is already kind of very interesting, is that if you take the product of a triangle and a hexagon, that's a symplectic ball. And that was the question that motivated this work. And Ostrover asked me 2 years ago, and we were able to figure out how to do this. But what's kind of interesting, we're still writing up the proof, is that to prove this, we actually have to use not only billiards, but this thing, the Toda lattice and some representation theory. And there's some hope that if you look at kind of the list of all simple groups, simple Lie groups, that you can get similar results for other products. And you can get a variety of polytopes whose product will be a symplectic ball. And I'm just going to end with saying that it's not extremely surprising these are balls. First, because you can, using billiard dynamics, you can see that they're equalizers of the Viterbo conjecture. So you can look here and look, OK, what's the smallest billiard? And what's its length with respect to the geometry of the other table? And you can compute that basically you get what you need to get to the equality. And even more, you can see Zollness. So kind of tying it up with what Lucas was saying yesterday. You can actually see that every point is on an orbit, and they all have the same length. So that's not true, of course, of billiards on the equilateral triangle. But if you change the geometry of the reflection law, instead of having a disk, you have this hexagon, then it is true that every point is on a closed billiard trajectory, all of the same length. So you can see Zollness here. But you have to put some serious glasses to see it. But anyway, so yeah, thanks for listening.
Thank you very much, Vinicius. Are there questions or comments?
Thank you for a very interesting talk. One question. So for the Mahler conjecture, yes, the lower bound, are there any results that the perpendicular, these sets are local maximizers using some perturbative theory, for example?
Yes, there are. I'm forgetting who did it. But yes, there are. I think it's actually not very old. I think in the last 10 or 20 years. It is proven that in the neighborhood of the Hunter polytopes, which are these kind of square, these pointier convex sets, that they are local minimizers. So yeah, there is a local theory. Yeah.
Thank you. It's wonderful to see, and it's sort of shocking because I'm from Stanford, where symplectic geometry looks completely different than the wonderful concrete math that you pose. And is this the same Hofer who does category theory and wrote those 2 giant volumes making math out of Yasha's pictures?
There are holomorphic curves,
Amazing.
Yeah, there's that, and behind, a lot of. So originally, symplectic capacities were defined. Well, you probably know the Gromov's non-squeezing uses holomorphic curves and kind of introduces algebraic geometry techniques to symplectic geometry. But then the Hofer-Zender, the Hofer school, at least earlier on, like in the late 80s and early 90s, was without holomorphic curves. So instead, they used some hard analysis. But then it actually eventually converged. And then, of course, Hofer and Eliashberg talked, and Dusa McDuff, and all these people talked. And then, but nowadays, modernly, all these symplectic capacities, most of them are defined using some Floer homology theory, where the pseudo-homomorphic curves are there in the differentials. So, and these are just spectral invariants of that homology. So yeah, this is maybe I'm just telling you what's happening above the water, And then if you go down to the deep sea, you see some ugly creatures.
Thank you for that.
I like creatures, but one basic question that occurred to me, and I didn't want to interrupt you. Are these capacities determined by their values on convex sets or not?
No, they're not. Yeah. No, they're definitely not. So, for example, I said that the theorem was Ecklenhofer, Holford-Zender, and that's because there were actually two different capacities that they proved earlier on. They were the same for convex sets. But in general, it's not so hard to construct capacities that maybe coincide for convex sets, but are always, I mean, we don't know any capacities that are different for convex sets, because otherwise that would be a counterexample to the conjecture that all capacities coincide, and that's still an open conjecture. But it's not so hard to find capacities that are different for sets that are not convex. So there are certainly examples of that. And there are applications. Sometimes you want to study a symplectic embedding problem, and then a certain capacity doesn't work, and you have to use another capacity. So that certainly happens.
Yeah. Vinicius, so can you show us how the shortest orbits look like in this last example?
How the shortest?
Orbits look like in this last example?
Yeah, so if you look at standard triangles, it's relatively well known. And when I say billiard orbits here, because I'm doing symplectic geometry, I have to look at all the billiards, including the ones that billiards people don't like, with the ones that go to the corners. So usually people, when they study billiards, they want to discard the orbits that hit the corners. But we have to look at them all. So if you look at the triangle, for example, a nice exercise is that the smallest orbit in the equilateral triangle, and actually in any acute triangle, is an orbit that bounces 3 times. So this orbit is smaller than the orbit that just goes like this. And it's maybe not so obvious. And maybe if you have good eyes and you could see that, but I had to do the calculation, the trigonometry here. So anyway, so this is the smallest orbit. But that's because we are looking at the standard billiards. If you change the disk to a hexagon, then these orbits are actually the same length. So yeah, so I guess, and then they come in a family. You know, it's not so hard to see that these things come in a family. So yeah. Mm-hmm.
So first, thank you for your wonderful talk. And my question is concerned about this R0. You proved that the product of the cube with it's a symplectic ball.
Yeah.
So because when you were talking about the Mahler conjecture, and you were talking that you have this upper bound that is already proved, and you know the upper bound is also a ball, but you know the radius. So I guess you probably should know these are 0, or is it important in some sense?
So the upper bound, so for the Mahler conjecture, we're really looking at a product of a convex set and its polar body. So we know the maximum of that volume is attained for when K is a ball. So actually you have the product of a ball and a ball. And the minimum is attained, or should be attained, I should say, a conjecture in general, but in dimensions 2 and 3, it's true. It's attained for when K is the pointiest that's possible, which is a cube, or a more general Hunter polytope. But it turns out that if you take the product of that and its dual, that's symplectomorphic to a 2n-dimensional ball. That's not true for the product of a ball and a ball. So what I didn't tell you is that if you take the product of a disk and a disk, that's definitely not a ball, and that's one of my results is actually to show that this is symplectomorphic to a toric domain that is kind of concave. So I can tell you about that another time if you would like. But anyway, the radius is not very relevant, because once you know it's symplectomorphic to a ball, and you know the volume, then there is only one possible radius of a ball with that volume. That's why I didn't emphasize what the radius is. And also for the product of K and K dual, the radius is also not important, because if you scale one with a certain ratio, then the other one gets shrunk by that same radius. So it's like really for the Mahler conjecture, what really matters are the shapes and not the sizes, the specific sizes.
Okay, so before thanking Vinicius again. I would like to give you a small gift.
Oh, thank you. So let's see what this is.
Yeah, I think we should know by the end of the week. Oh.
Oh no, let's see. Oh, you don't want to see? Wow. There's a Möbius band.
Okay, so let's thank Vinicius again.